Okay, we've arrived. We're going to talk in this hopefully very short video about the cardinality of sets. I just want to get the terms laid out, and then we'll talk a little bit in later videos about how we relate the sizes of sets. In short, what is cardinality? Well, the cardinality of a set is more or less its size. Right? That's what we mean by cardinality. We use the word cardinality because, as we'll see, what we mean by size doesn't have great analogs in the real world, right? The understanding you might have about size in the real world isn't going to exactly apply here. Okay. So how does cardinality work? Well, the idea is that if S is a set, then this, which looks like absolute value, that denotes the cardinality of S. If S is a finite set, the cardinality of S is just a natural number. So, the cardinality of the empty set is equal to 0. The cardinality of the set containing true is equal to the cardinality of the set containing Prof. Greenberg, is equal to the cardinality of the set containing Pomona College, is 1. The cardinality of the set bool, that is to say the cardinality of the set true, false, is equal to 2. The cardinality of the set of the type we define in Coq of bases, right? That is the cardinality of the set A, G, C, T is 4. It's the number of things in it, right? And so, for example, you could prove a theorem saying that for finite sets A and B, the cardinality of A union B is less than or equal to the cardinality of A plus the cardinality of B. Or more precisely, the cardinality of A union B is equal to the cardinality of A plus the cardinality of B minus the cardinality of A. That's not a triangle, folks. I know my handwriting's bad, but you don't need to remind me, whiteboard. Right? So I'm not going to prove either of these now. They would go just sort of by induction on the cardinalities of A or B. It's worth noting on this less than or equal to, which corresponds to this. The idea being that if you have common elements in A or B, then the cardinality of their union won't just be the sum of their individual cardinalities, but you'll have to, avoid double counting. Okay. That's finite sets. Cool. Right? If you think of these as lists, like we represented them in Coq, the cardinality of a nat set, a list of nats, is just its length, assuming that it's set-like. There's nothing more to it. It's very simple. The hard part of cardinality, the part that's really just hard to get your head around, is cardinality of infinite sets. So let's start with the cardinality of nat equals the cardinality of n. So there's no number we can write here, right? There's no finite number of elements. So what do we name this thing, right? What do we want to call this thing? So, it's tough. These ideas were first studied by somebody named Georg Cantor. He was a big deal, it turns out. Super smart guy. He's the one responsible for a huge amount of the set theory we know today. When he first discovered all this stuff that we're about to learn in this and the next few videos, people freaked out. They thought he was cheating. They thought that he was breaking all of the rules. They thought that this couldn't possibly be right. You shouldn't even talk about infinities. They got mad. Like, they were extremely mad online. So, people have gotten used to it. People now realize that Georg Cantor's arguments are really the best that we know of. And what he did, he said, okay, cool. Just to give it a name, We need to name this cardinality of this infinite thing. The naturals are kind of the smallest infinite thing we can imagine. So he's going to give them a name. Aleph null. Okay, so my family goes back rabbis as far as the eye can see, and they were all going to be embarrassed by the way that I wrote that Aleph, because I actually really only write Hebrew cursive. So if you want a nicer way of writing Aleph, so first off in LaTeX, this is just this Aleph. It's the first letter of the Hebrew alphabet. You might think alphabet, Aleph bet. Just gonna say that sort of the Phoenicians and the general people in the Levant there were kind of the OGs on the alphabet scene, and the Greeks are kind of late comers. I'm just gonna put it out there. I think that that they're just a little late. In any case, this is Aleph null. If you want a nice way of writing it cursively, there's two things you can do. One, you could just do this. Aleph null. I find that really hard to read. So in modern Hebrew, in cursive, you would write it this way. And that looks really weird, but is maybe a nice shorthand if you feel more comfortable doing it that way. You can look up online the way that these are really supposed to look. I'm going to do my best right now. So it's something like this. And then, what is it? What are we really talking about? Something like that. Yeah, all right, let's get in there. And then Aleph. Aleph null. Also called Aleph not. If you want to feel like extra British, or you're feeling naughty, you could call it Aleph not. Really, whatever does the trick for you. Okay, so we're just going to call this thing Aleph null. We don't really know a lot about that yet. That's fine. We might wonder, for example, knowing other forms of numbers, what is the cardinality of the integers? What is the cardinality of the rationals? What is the cardinality of the reals? And then there's other infinite types we've seen, right? So like, what is the cardinality of list of bool? What is the cardinality of list of gnat? Right? These are all really tricky questions. So I'm going to tell you the answers now because you're going to be really surprised. And then we'll see how we find out those answers later on. Okay, what is the cardinality of the integers? That one's going to also be Aleph null. What about the rationals? Oh yeah, we're going to go Aleph null on that one again. What about list of bool? Oh yeah, how about a little bit of Aleph null? That's a really wonky Aleph. Okay, what about list of gnats? Did anybody say Aleph null? What about the reals? That's going to be 2 to the Aleph null. Now, there's a famous question called the continuum hypothesis that says, hey, here we have Aleph null. It's going to be strictly smaller than 2 to the Aleph null. Does anything go in there? And, people don't know. We don't know the answer to this question. Saying no is the continuum hypothesis. And we just the set of mathematics that we know about doesn't let us have an answer. So people will do math where they'll assume the continuum hypothesis, where there's nothing in between Aleph null and 2 to the Aleph null. They'll call that accordingly Aleph 1. And then people will say, no, you know what? I don't believe that. I'm going to assume there are other things in between. Right? And both of these are perfectly valid mathematics. This may not be a thing that you expected to learn about math at any point in your life. That, there are questions that are simply open to debate. Right? There are things that we don't know the answer to. But here we are in actually a computer science course, and we've already found one. I find that to be actually really miraculous. I think that's just really incredible that's possible for us to, in really not that much time, 12 something weeks, to have been able to explain, oh, this is a question that math just doesn't know the answer to. Pretty cool. Okay, so in the following videos, I'm going to talk about how we can establish relative sizes, right? That is to say, how do we know this bit, right? That's going to be the next two videos. And then after that, how do we know this bit? That's going to be the video after that. So I hope I've piqued your interest with this counterintuitive result, and I'll have more videos coming at you soon. Take care, everybody.